unrealistic expectations, that you're not held to account for early optimistic targets that somehow get turned into estimates, and such that you're not ending up, you know, having a very dissatisfied client and users just because you've made the same mistake made here in class with estimates that are too narrow, okay? So we're going to be talking about a set of best practices today for estimation. Why am I introducing this material today? I'm introducing it because we are going to be needing to have some estimates as part of your milestones going forward. It's going to be a pretty important component of deciding whether or not certain features are doable within the time frame of a given milestone, a given incremental delivery. It'll be important for deciding how many features you could implement for the client, for example, for deciding how much to load in one person's plate, etc. So we're going to talk about a few best practices and just a couple of ideas, making sure that targets and estimates are not confused, making sure that you give range estimates rather than simple numbers to estimate something. Rather than one number, you give a range, best and worst. Techniques for making sure that your estimate ranges are not overly narrow. Not only not off, but not overly narrow. That we don't have too much hubris, too much confidence in our degree of knowledge. We can avoid some common mistakes associated with estimation. Arguably the most important one, however, will be the technique of what's known as decomposition. Taking apart a plan into its pieces and estimating each of those and then coming up with an estimate for the whole, rather than trying to estimate the whole thing at once. Turns out estimates are much more reliable if you break it down into small pieces that you can really think through in a very, very clear way. Okay? So we're going to be hitting these points today as time allows, and we may finish up next time on this. Okay, so I'd like you to, while I'm talking, maybe you could pass up the small quizzes. Again, I'm not going to mark you on the accuracy of your answers. I'm simply going to record, make sure that you fill in the blanks, and that's going to lead to the marks. If you could actually, if you could, someone could go around, that's much appreciated. Thanks. Okay, so let's talk about estimation. Why do we do estimates? Thanks very much. Anyone else still have theirs? No? Okay. So why do we undertake estimates? Well, there's a variety of reasons at different stages of the software process. One is we need ongoing estimates of time in dollars, and these are particularly key if we are running late or running over budget, but they need to get done often early in a project and then for an incremental delivery on an ongoing basis. Rough estimation is key for even scope and go, no-go decisions. Do we want to take on this project? Do we want to add this feature in, or is it too risky for this next incremental deliverable? For assessing the level of risk involved in a project and in planning deliverables. What are we going to do before what? Being able to do some simple back-of-the-envelope calculations can be very helpful. The methodologies that we're going to be talking about today can help us prevent against dangerous psychological tendencies by which we fool ourselves. And I want to start with an important distinction between three types of quantities, or three types of components or elements that go into software project management that all relate to time, all relate to what gets done. The three of them are an estimate, a target, and a plan. Okay? An estimate is an honest, realistic assessment of how much resources, often time is the most critical one, but often dollars, people are also considered, to secure some objective, to secure some implementation of some requirements. For example, within a given set of quality constraints. So an estimate is a careful assessment. It's realistic of how long it might take. A target describes a desirable goal after which we'll shoot. We'll shoot to get it done by then, but we can't be sure. Sometimes that's given to you. See if you can get it done by the holiday season. Sometimes it's something you choose. We've got good morale right now. We're going to see if we can finish up this next milestone a week early so that we can have a demo session with the client, right? So target is something we'd like to make. It's an aspirational goal. It's something we'd very much like to achieve. But it's not necessarily something that we believe is a realistic assessment of how long it's going to take. It's something we'll try to do. A plan is a detailed recipe for how we're going to achieve this objective. And we're not going to be talking so much about the plans except in as much as they influence estimates today. So a couple key considerations. This is really important. This is highly testable. So there's a couple tendencies within people and within projects that can make estimation quite tricky. First of all, estimates have a strong optimistic bias. Okay? Optimistic in two senses. One is they often estimate too low. They think that you can be more productive than you really are able to. They don't consider certain factors which end up taking a lot of time, etc. So they're optimistic in this. But they're also optimistic in terms of over-optimism about our level of precision, about how accurately we can bound something, about how tightly we can bound something. They're optimistic, they're over-optimistic in the sense that we have undue hubris about, or undue degrees of confidence about the level of accuracy of our estimates. Okay, so we give estimates that are too low and range estimates that are too narrow. We saw that earlier, right? With this thing here, we should have expected many up in this 9 region. 9 of those answers correct out of 10, and instead we had many that were far below that. A key issue here is when and by whom an estimation is performed. Who's performing it? Is it the technical folks or their manager? This is really important. And you don't want the manager to do an estimate, hand it to the technical folks, and expect them to live by that estimate. Another thing is often technical folks bow to pressure, particularly from above, as to what estimates to take on, and they allow targets to become estimates. And it's given repeatedly to them. We need it by December. When is it going to be ready? Well, I think it's going to take till March. Well, we need it by December. When will it be ready? Well, maybe we can do it by late January. That's not acceptable. We need it by December. When are you going to have it? Well, maybe we can do it if we all work over the holidays, maybe we can do it by the end of December. Okay, good. I'll put down December 15th. And you can have a few weeks slack time during the holidays to finish it up in case you're late. These things go on a lot. Technical people aren't always as savvy in the political sphere, and sometimes you get these things hammered down. And what's worse is quite often that manager who's giving you those targets may be promoted to a boss and moved to another area of the company by the time that your project is deemed late. Maybe it comes in early March. But as far as they're concerned, it's late. Because December 15th is the target date. So you don't want these things to become estimates to be handed down. And you don't want estimates to be turned into commitments. look, this is a best guess right now. There's a lot of uncertainties still. There's a lot of technologies here we've never worked with. It's not a commitment. It's a good faith attempt to estimate, to try to reason through in a careful fashion, in an accurate fashion, how long it will take. But there should be wide ranges of uncertainty, and it's not a commitment. It's something we will, we believe it will take this time, but we'll re-examine it over time as information comes in. The real problem here, and the main reason I'm giving a lecture on this topic, which may otherwise seem very dry, is that software engineers are just terrible at estimating historically. So I think I told you the story that when I wore a young man's shoes, the saying was that you should, to get an estimate for how long a given task would take in software, say a given project, you should ask the person how long it's going to take, get a point estimate of how long it's going to take, then multiply by 3, shift up to the next higher units, and add 1. So if the person says it takes 3 days, multiply by 3, get 9 days, switch it up to weeks, 9 weeks, and add 1. 10 weeks. Sounds good. So, Tom DeMarco comments, the most common definition of estimate is the most optimistic prediction that has a non-zero probability of being true. And so we often give this very hopeful sense. We can't think about why it couldn't be, we can't imagine a situation where it could be less than that. I think it has some chance of hitting that, so we give this out. And he says, accepting this definition, if you're willing to consistently give estimates that are on the early side, maybe because that's what you feel the person wants, maybe because you want to feel good about your software engineering skills, you can think, I can do this quickly. If you accept this definition, it leads irrevocably to a method called what's the earliest date by which you can't prove you won't be finished estimating. So the earliest date that is even vaguely plausible, that's the one you end up giving. That's a real danger. So a lot of bad estimates written. So when you read about software projects that are terribly late, you have to ask, according to whom are they late? According to what criteria are they late? And perhaps it was due to a sloppy estimate as much as a real problem inherently in the problem. The problem is that people make plans around these things. Whole divisions of the company may be anticipating this new IT system being in place. And so they stop using the old system, are waiting to cut over to the new system, and all their plans are thrown out of whack because the new system is 3 months late. And the whole company's now been affected. It's not just a matter of the IT folks. So, even if it's due to a poor original estimate, there are big consequences, very material consequences, sometimes millions of dollars. Okay, so let's talk about optimism. Okay. So there's 3 dangers of optimism. Well, even if no one ever estimated a problem, even if you're not going to go and actually perform an estimate on your project, the problem is that projects have a long tail in terms of when they get delivered to the right. If we draw out a probability distribution for when a project will finish, empirically, even if no one's going and estimating it, we look at how long projects take to finish, you will find a distribution that can't go very far to the left because you can't finish yesterday, a project that started today. But it goes a long distance to the right. Okay? It's a long tail out here. This is probably underestimating. It's heavy-tailed on the right-hand side. And what that means is that much higher chance of being way off on the upper side in terms of how long it takes than on the lower side. On the lower side, we're bounded by the fact that, can't complete instantly, right? So there's an asymmetric distribution of how long things to take. There's also asymmetric psychological tendencies. Our estimates tend to err on the side of being too optimistic, being underplaying how long it's going to take. And underplaying the level of uncertainty about that estimate. Either one of them by itself wouldn't be totally disastrous. If you were estimating too little, but you had nice wide ranges of uncertainty about that, hey, you know, you have a worst case that's really, really large. Despite that, you should be able to work with it. But if you had estimates that are right on the money, just too narrow, you wouldn't be doing too bad either. But you combine the two of them, you're giving an estimate that's way too favorable and it's way narrow. You're saying, I'm extremely confident about this number that's almost certainly wrong. That's bad news. It's really bad news. And the worst thing is, folks, suppose your estimates were off and too narrow on the upper side. In other words, you are always saying it's going to take longer than it really does. And you compare that to the consequences if you're off on the lower side. You're saying that it's going to take less time than it really does. You're going to end up with clients that are much happier with the first of the situation. If you're always estimating it's going to take longer, you actually finish it up early. It's not nearly as bad. Okay, they budgeted all this extra time and now that's not needed. Well, companies can often work with that. Organizations can work with that. People can work with that much better than if you're counting on it and it's late. Right? So, if it comes in early, great. It's not like a train. It comes in early, you miss the train. It's okay. It comes in early, comes in late, but or a bus. But it's more that, okay, if you're late, it's you know, all these people have been counting on around it. They've been waiting to take advantage of it. Whereas if it comes in early, it's a little bit of an extra bonus. The team can always be shifted to something else, and things can be scrambled to take advantage of it sooner. Okay, so let's take a look at this asymmetry. Here's a situation of, so these are real world projects. This is an actual organization for IT project. And you can see here's the target completion date in down here in days on the bottom side, and here's the actual completion date on the vertical axis. So the horizontal is target, the vertical is the actual. Does anyone see an asymmetry in this graph? Where would projects fall if they came in exactly as targeted? On the diagonal, right? Their actual would be the same as their target. Their actual would be the same as their target, right? And where instead do they fall? Almost entirely above that line. What does above the line mean? They're late. They require longer than expected. Now, some of them it's not too bad. You take a look at this one out here at 220 days, and it took 260. Okay, it's 40 days late out at 220. So that's a little bit less than 20% late, but it's not doing absolutely horrible. But here, some that were estimated to take, 10 days, and they took 80 days? Can you imagine that? So it was supposed to take 7 days, and it took 265. No wonder they didn't want their company name associated with it, right? Now, I'll tell you, within my professional time, I haven't quite seen that one, but I've definitely seen some where a task that seemed like it would take a week ended up taking 3 months. Because you're counting on a certain size. Well, of course the system's going to, remember one project, of course Crystal Reports is going to be able to handle this situation, right? And you go into, it only handles it for Oracle 8.3 and above? We have 8.2 right now? Well, okay, we're going to do this workaround. Oh, the workaround isn't working either. you know, oh, we're encountering this weird bug in this, and oh, we're going to have to do it in a different technology altogether. We're going to have to ditch crystal reports and directly, you know, write numbers into Excel. And then we have an issue because we can't get the certain feature we are counting on for crystal reports right. And it just balloons, one thing to the next to the next. So you do get situations where things get amazingly off. And if you go talk with people in industry, they can probably tell you about those projects. It just was a cascading series of problems. Once you start replanning on the fly, you don't have time to really think things through. You can make decisions which are pretty rash, and they end up chewing up a lot more time. So this is a very real problem in industry. The problem is that if we come in here in a situation where we overestimate, badness is often not nearly as pronounced as if we come in with an underestimate. In other words, we're in a situation where we underestimate, people are counting on it, it's often much, much worse. And one of the things that makes this difficult is that over time, we could plot this out for a milestone, for example. We start with very, very wide estimates of how long things might take, and we go down, we get more and more confident, but more and more confident, ironically, at a time where we can't really do much anymore to change how long it's going to take. Early on, we can change the requirements we're going to implement, but we're very uncertain how long it's going to take. By the time we're clear about how long it's going to take, we're not going to be able to change those requirements so easily. So why are people so consistently optimistic? What things are they ignoring? Well, here are some of them that McConnell has listed. There's a lot of sort of incidentals, things that you don't really have a habit about thinking about when you give estimates. They include ramp-up time for new team members, time to train people or mentor them, data conversion, you know, to convert over to the new system, for example, installation issues and making sure installation works on all the different devices in the company, time to support the build and maintaining this, creation of test data, integration work between different components, communicating with the client. Maybe the client you write to and doesn't write back in a timely fashion. You're counting on them to respond quickly, and it doesn't end up happening. That's an issue of risk management, but it's something which might have been omitted from your consideration of the estimates. You can go back and see those in the slides. Here are some more. People ignore the fact people get sick. That people are off for training. There's holidays in there. Now we're getting into the holiday season, perhaps. You know, we're going to have downtime due to spring break next week. Teams in this class have forgotten that and have ended up flat on their back 2 weeks after spring break, being about a month behind what they anticipated. Holidays also flow out schedules. Imagine a project that's supposed to finish up in mid-November. It gets delayed until mid-December, and then it starts getting delayed again, and suddenly it's not going to get delivered until mid-January because of the holidays. Okay, so you know, here's a bit of a checklist that I think you could do well to put into place for your projects. So, is what's being estimated clearly defined? Do we really know what's being talked about here? Is it clear in the person's mind? If not, it'll be much more uncertain than we might think. Does it include all the work needed to complete it? Really, to finish it? Does it include, for example, testing? Does it include peer review? Does it include the time needed to integrate it with other components, etc.? Is it broken down in enough detail to expose hidden work? This is something we'll be hitting on next. This is why we do decomposition. One of the big reasons we do decomposition in our estimates. We break things down into pieces because if we're if we're not thinking in concrete terms, it's easy to fool ourselves. Ladies and gentlemen, in life in general, it's easy for people to get fooled by abstractions, like sort of fuzzy, broad ideas. When you start thinking in very concrete terms, often you can think at a much sharper level. And when it comes to estimates, people can be terrible at breaking down, at giving an overall estimate of a system. But if you start breaking down into small pieces, things get better. Errors cancel, and you're thinking in concrete terms, okay, exactly how long that's going to take. You're thinking in operational terms. How long would it take me to do that? Well, let's see. I'd have to look up information on this API, and let's see, I'd be using JavaScript. I haven't used that in several years, and I tried something a few months ago. It ended up taking, twice as long as I thought. And so you start thinking in very operational terms about what needs to be done in each successive step. Okay. A key thing that we're going to be talking about is, does the estimate include a best case, a worst case, and a most likely case? We want to make sure that your estimate is informed in terms of its upper and lower bounds. And we're going to be pushing on this issue of, is the worst case really the worst case? Is it something which is too narrow, for example? Okay, I think I'll go light on that. Okay, so if you go talk with many companies, including companies here in town, you'll find that many, for a purpose of estimation, adhere to what's called the decomposition-based technique. So this sort of technique involves, if you want to estimate how long a task is going to take, you first break that task down into its constituent parts, into its pieces. What do we actually need to do? What are the steps by which we need to accomplish it? And that helps us, again, think more concretely, and helps mean that when we give out estimates, they'll be about things we can really think through. And those estimates will often, errors in those estimates will often cancel. Not always, but often. Okay? So here we're systematically identifying the amount of work and or equipment required. And we're trying to create a list that's really specifies what needs to be done. Okay? We're then going to take those estimates on the pieces and turn them into an estimate for the whole. And there's an art to that, or there's almost a science to it we'll be talking about. Okay? So the point is, you're thinking things through more completely. So you may wonder reasons why I'm asking you to undertake an incremental development process for this class. One of the reasons, of many good ones, is that when you're doing things week by week or every few weeks, and you're asked about a task, it's harder to fool yourself thinking about how much work you're going to get done this week than about the semester as a whole. So teams in this class in the past, look 7 or 8 years ago, they'd often just work towards some overall goal for the semester. There wasn't, incremental deliverables were encouraged but not required. And the teams would often get far, far, far short of where they intended to go. Why? Because it's much easier to fool yourself as to how far we can get. If you're thinking about your work in the next week, you start thinking about factors like, well, I've got this big report due for my English class on Friday. I have to leave for my sister's wedding this coming weekend. I have internship interviews I've got to go to. I'm not going to have much time this week. 2 members of our team are sick. So the estimate you give from that is going to more likely, because you're thinking in very specific terms, it's much more likely to be grounded, to be accurate, than a situation where you're trying to imagine over the next term. You're not clear about people's other commitments, who's going to get sick, what social obligations they'll have, how many weekends they'll be available, what they're going to do for spring break. you've abstracted away from all of that. You're just thinking in general terms, and it's very easy to fool yourself by a factor of 2 or 3 or 4. How far are you going to get? And if you don't think I exaggerate, there's one 8-person team. They got less work done in the semester than I think 2 motivated people could have gotten. They went to create for CSSS, no less, create a locker and book sort of checkout system, so you could rent lockers. It was just amazing. I think at the end they couldn't even rent a locker. Just said like what lockers are not currently rented, and you couldn't even rent one, something like that. This is a 3 thumbs up, system. Bright people, some of them working in industry today, across the country. Bright, bright-eyed and bushy-tailed. But they had a devil of a time, and part of it was they couldn't estimate effectively how much they were going to get done during the term. So, sometimes what happens is you get out in an estimate on particular features, for example, and you have some error. You're off on those estimates, but the errors tend to cancel somewhat. And so, you get in a situation where the raw error that you get off for the whole is less than the error than various parts. Okay, so there's a couple of issues with decomposition. Decomposition is an extremely valuable technique, and if you are going to be doing estimates in your project, you should be using it, very reliably. When you're going to give an estimate for something, break it down into its pieces. Okay? And estimate each of those, and then you're going to combine them to get an estimate of the whole. The problem with this technique is, even with decomposition, we tend to be too optimistic. By 20 to 30% in one study that was done. So the tendency here is for developers to give a best case estimate rather than a median or mean. We like to think about that nice, smooth, typical case. We think it's typical, where we're just humming along, things are going well, we don't have to reinstall Windows on our machine halfway through, our account doesn't get hacked, we remember all our passwords, Merlin isn't sick, all these things we think of as the typical case. So we're too optimistic. Client pressure and pride pushes to smaller numbers and towards estimates that are too tight. Surely I know my Greek history well enough to know when Alexander the Great was born within a century, right? Just no way I could be off, by more than 100 years. He was a contemporary of Cicero, wasn't he? And then it started off, confused Alexander the Great with his father, Philip of Macedon. Well, okay, maybe Darius the Great or something like that. You're off. Your pride leads you to think your estimate is more narrow than the range estimate is more narrow than it could be. So one way we deal with this is providing range estimates, which help avoid just naturally, if we're asked to give one number, we want to give a number that sums up our confidence, sums up our sort of sense of optimism. We tend to do that. Maybe it's not a conscious thing, but we tend to do it. We don't want to look bad from this one number. So instead, you force people to give ranges. You force them to give the worst case and the best case. And they're less likely to reflexively fall into this situation where they give a really small number. Maybe the best case is small, but the worst case you hope will be a sum of all fears. And it's going to be quite broad. The problem is that even with that, we are too optimistic in our ability to estimate. Is it professional pride? Is it the sense that we know what we're talking about, and we can't be too far off, but it's almost always too narrow. Okay. So point decomposition estimates. If you're asked to give one number, you should be concerned and instead give a range estimate. If you're asked to give a single number, that's a sign that there's real danger. Give a range estimate, though, because otherwise you may reflexively give something close to a best case estimate. Okay. So let's talk about these range estimates. So range estimates make explicit optimistic assumptions and pessimistic assumptions, and some expected case. Okay. Some mean, average case, expected value. Sometimes you hear about other varieties where it's the median case, the case where 50% of the time it's less than that, 50% above that, not as stretched out by upper values in the upper side, for example, or the most likely case, the mode of the distribution. Now, when I describe optimistic estimates, pessimistic estimates here, it's telling and interesting that with this little quiz, I wasn't asking you to estimate how long it would take you to do something, right? So it really didn't have the aspect of professional pride tied up in giving optimistic estimates, lending you towards optimism. After all, you don't particularly care if Alexander the Great was born in 500 BCE or 100 BCE. It's not a matter of your productivity being questioned, right? Now, if these were questions about how quickly you could write a quicksort routine, or how quickly you could implement to me a binary search, or a fully debugged binary search, or how fast you could implement a hash table in Java, if I had asked those things, those would have involved some misestimates because you want to feel, oh, you're a good programmer. But even so, the range estimates that were given tended to be too narrow. Okay, and it's an interesting commentary on this. Forcing someone, when they are giving estimates of their own work, their own team's work, or their own personal work, to think these things through, make it less likely that they'll just accidentally substitute a best case for the expected case. It also gives client information regarding uncertainty in estimates. It gives the client a clear signal. If your worst case estimate is 5 times longer than your best case, it's a signal that you're not sure, that there's risks, right? There's risks involved. You're not certain. Things need to be investigated. And that may be something a client picks up on and asks you, hey, try to make it a priority to narrow that down. See if you can, what are some of the risks that you're uncertain about? And you say, well, I don't know if the certain technology we've settled on is going to work out. And then you say, well, look, why don't you take a week now, do a prototype, see if it's going to work, then come back with an estimate. Okay, that's a constructive thing. Lets you narrow your range by investigating risks. So that's good. And finally, and this is very important, it decreases the risk that an estimate will be taken as a commitment. That your estimated value will be say, okay, you're promising to get it done by then. If you give a range, it's clear, look, this is a sense of how long it might take, trying to be accurate in how long the estimate is not a commitment, right? And what we're hoping is that our estimates over time consistently fall within our range. The actual values fall within our ranges. Over time, our ranges will get smaller and smaller as certain risks are eliminated. When we're uncertain about the requirements, how they're going to exactly shake down, there's going to be broader range associated with our estimates than once the requirements are complete or when the architecture is completed. We see just how complicated it is, okay? Okay, so let's talk about range estimates a little bit, and we're almost certainly going to need to finish this up. It's time. So, we're going to take a look at a situation where decomposition has been used And it's provided, people have provided a best case, most likely case, and a worst case. And then sort of an expected case, a mean, okay? So here they've broken it down by different features, and the goal will be to get an estimate for the whole thing. Breaking it down into features is a strategy. It's a means to an end, where the end is an estimate for the whole. How long will this package of features take? And what we're going to be talking about over the next 10 minutes is how to do this well to make sure the best and worst case are kept accurate, and how do we then turn that into an estimate for the entire thing, such that that estimate also captures the uncertainties. Okay, so I've stressed, and it was, I think, brought out to you by the exercise, range estimates often far underestimate the width of intervals. And you know, you might want to specify along with them some of the reasons why you've chosen the best and worst cases. Like, what is it that you're concerned about? Okay. And then finally, you're going to need care in going from best cases and worst cases for each subpiece into a best and worst case for the project as a whole. Okay. Okay. So, for one thing, is you might want to make best and worst case estimates have explicit sort of rules associated with them. I gave you 90% estimates as a request earlier on. Best case estimates, you know, you might have something much more stringent, like only less than 1% chance that the actual value falls less than less than 1% chance it's more. Okay, and we're going to be dealing with expected cases and calculating them. So let me ask this. I'm going to pose a question. So here we have these best case estimates and worst case for each subpiece. And suppose that I were to come along and say, great, you're giving me the best and worst cases for each subpiece. To get the best case for the whole project, I'm just going to total up the best cases for the subpieces. And the same thing for the worst. Is that likely to give a reasonable best case for the project as a whole? Suppose I have this decomposition, all these features, best cases for each, I just total them up, and I get a best case for the entire project. Is that going to be a reliable way? Why not? Why would that be dangerous? Yeah.
Because the expected likelihood that all of the best cases will be true is much less than the expected likelihood that any individual best case.
Yeah. So maybe, well put. I mean, in any one case, you know, that may take you less time than you thought, and some others might take more time. The chance that all of them are going to line up like that to systematically hit their best case is vanishingly unlikely. It's extremely unlikely. You're going to be lucky enough to get, you know, your best case for all of these in a row. So it tends to underestimate, which is dangerous, especially dangerous, tends to underestimate how long it will take in the best case. A realistic best case, say that, you know, less than 1%, less than 1%, where was it? Less than 1% of the time it falls beneath that. It's not going to be given by this. This is going to have maybe a 10 to the minus 20th chance, you know, that it's less than that. And the same thing with worst case. It's unlikely you'll hit all of those bad things, although it's a little bit more plausible often. So we can't just sum up the best cases. So what do? Well, what we do is we're going to estimate for each piece the expected value, the mean, okay, for each piece. We're going to total up the expected values for some pieces. And then we're going to derive the variance of the whole from variance for the pieces, okay? And that makes some assumptions, which could sometimes be questioned, but it's much more reliable. So we're going to get a variance for the whole, ladies and gentlemen, a variance associated with this, and a mean associated with it, an expected case, an expected value associated with this, and then try to estimate from that sort of the degree of uncertainty about the whole, okay? So we're going to end up getting sort of a standard deviation here for each piece using a formula we're going to be giving from the best and the worst case. We're going to derive a variance, sum those all up, and arrive at a standard deviation for the project as a whole. And similarly, we're going to sum up the expected value. Okay, so the idea here is you estimate three things, ladies and gentlemen. Best case, worst case, most likely case. The mode. Single case that's most likely. And an assumption that's advocated here by some prominent authors is you assume a so-called beta distribution, which is a distribution that can be skewed, say on the right-hand side with a heavy tail, for example. And you can estimate the expected value from the best, worst, and most likely cases using formulas like this. You'll notice that this is sort of a more conservative form of it. So the key thing is we're going to estimate the estimate the expected value for time for each subpiece, and then we're going to be able to total those up. Okay? So we're going to go from best and worst cases and most likely cases to an expected case. So best, most likely, worst, and we're going to get out, we're going to estimate all of these via that formula. Okay? This one or this one. I'd prefer the conservative one. Okay, and you can then total these up. These are means, and they can be totaled up. Okay, these guys are the ones you directly computed. So here's the expected case, and you've totaled that up. These are just the ones that you had specified as part of your estimates for each of these subpieces. Does that make sense? Okay, for each subpiece, we're going to get this mean, total them up to get a mean for the project as a whole. So that's great, but there's another key piece missing for the project as a whole, which is the variance. How uncertain are we about this point, okay? The fly in the ointment here is we could simply apply a formula directly if our best and worst case estimates were indeed 3 standard deviations out as sought. If they were indeed far enough out that we have a very small chance of falling beneath them, less than 1% chance. But the chances are that they're not that far out, okay? Often we far underestimate the width of the intervals. So we're going to impose a correction factor. Now, I will finish this next time, but I want to tell you what happens once we put in place a correction factor, okay? We're going to put in place a correction factor, and that's going to allow us to derive these variances for each of these subfeatures, okay? And we can then sum up the variances. That's assuming independent errors, which can be problematic. Sometimes the same underlying problem, a flaky third-party piece of software we're using, can make our debugging slower, our testing slower, our coding slower. Maybe it's poorly documented, and it's going to throw us off on all those things. But here you could total up the variances, and then find the standard deviation from the whole is one approach that's suggested. Okay, so the idea is, folks, that you'd have a best and worst case and a most likely case. You derive the means, you total those up from the best case and the worst case, by correcting for our overly optimistic narrow ranges, we can arrive at an estimate of standard deviation, and then the variance, sum those up, get a variance and then a standard deviation for the project as a whole. And once we've done that, we have an expected case and a variance for the project as a whole. That gives us some ability to say, okay, how broad is our range? That's the basic idea. We'll talk about this a little bit more next time before we go on to a different project, or different topic. But this afternoon, first, I'll be hearing about the deliverables. Okay? So that's all for today. We'll see you at 4 p.m. to hear from you.